Welcome to the last presentation as we develop our quadratic skills, or skills with a quadratic function, before going on to some fun stuff where we use those skills in problem solving. Have a look at around the screen here, and can you answer the question? How can you tell? How can you tell what? Well, down here, these graphs, these quadratic functions, when graphed, don't cut the x-axis. These just touch the x-axis, and these cut the x-axis twice. Is there a way you could have told that just from the quadratic formula here? Is there a way? Okay, budding young mathematician, surely you'd like to know what are the secrets that you have to unlock about A, B and C to relate that function to its graph. Let's have a look at what we've done so far. If you're looking for where the graph cuts the x-axis, you're going to put the function equal to naught, because all on the x-axis, y is naught. And we know now there's a formula for this. There's also factorizing, which you can use to solve this. And we've been doing that and completing the square. Okay, is another way of solving that equation. And there's the general formula that we spoke about in the last presentation. So, what is it about this formula that might distinguish between those three scenarios? How can it be that it does not cut the x-axis, does not cut, or touches, cuts once if you like, and then cuts twice? Looks like there are three scenarios coming out of this formula. What could give rise to that? Can you think? What's probably the most interesting part of this formula, would you say? Oh, I think this one. The square root. And I think there are three different sort of considerations with the square root, aren't there? When you have b squared take 4ac as a negative, you can't work out in the real number world the square root of a negative. So therefore, the Cartesian plane is a set of real numbers in x and y, and therefore there wouldn't be a solution. The square root of a negative, no real solution. That might be up here. If that b squared take 4ac turned out to be a negative, you wouldn't be able to find the square root of it. There'd be no solution. It would not cut the x-axis. What about just touches? Can you think of what number would be in here if you only had a touching point? One solution. Oh, maybe equals 0. So does not cut. The number in there would be less than naught. If you only had one answer, if this was 0 in here, square root of 0 is 0. So the answer would be neg b over 2a, because neg b plus naught and neg b take naught would just be the neg b. Alright, are you getting the hang of this? This square root in here is causing us some interesting mathematical results. Cuts twice. Well, if b squared take 4ac was greater than naught, we'll put that over here, or positive, you'd have neg b plus that number and neg b take that number. You would have two distinct values, and they would be the two positions where it cuts the x-axis. So this little dude in here is pretty important, and I guess if you've looked at the name of this presentation, you might have already realised what we call it. Let's come down and have a look. There it is there. Okay, the discriminant. And these screen clippings are from Hayes and Harris, so it'd be good to have their book close by there. The discriminant. It helps us discriminate between the three graphical scenarios, if you like. Okay, and here it is. We use a Greek capital delta for the discriminant, because this is equivalent to D in Greek, and that's what the discriminant starts with the letter D. And it's the values b squared take 4ac. And the reason why that is so important is we're trying to find the square root of it. So we're really looking at the implications of the square root function in this formula. It has some implications because it is not defined for all real numbers. We've got to go into complex numbers and so on. Okay, So let's summarise what we've just done. If the discriminant is naught, you just get neg b over 2a. It's the only solution. Or a repeated root, or a repeated solution is another way of putting it. Or a double root. The saying only is probably not the best way. One of these two is better, because in a quadratic equation we have a square on the variable, and we should explain why there are or why there are not two roots. So there are actually two solutions, but they are repeated here, or a double solution. Okay. In the case of the discriminant, this thing here being a positive, you'll get an answer. So it'll be neg b plus that answer, or neg b take that answer. So there'll be two distinct real roots. And that will mean the graph of the function will cut the x-axis twice. If the discriminant is less than naught or negative, you can't find the square root of negative. So in this course, we could say there are no real roots. If you go on, there is a number, the imaginary number I, which is used to represent the square root of neg 1, and so you could have, and that's called complex number theory, and you could have complex number roots, neg b plus that and neg b take that. It would still have no intercepts on the x-axis, because although you can get a complex number or imaginary number to represent it, it isn't a real number. It's in the imaginary or complex number theory, and when you're looking at the graph of a function, you're talking about real numbers on the x and y axis. Okay, and then something down here that Hayes and Harris have got is interesting. If a, b and c are rational, that's the numbers in your equation, whole numbers or fractions, or the coefficients in your equation, and if the discriminant is a perfect square, so if this thing, you can find the square root of it perfectly, then the equation has two rational roots. That is, won't have square roots and they'll be whole numbers or fractions, and you would have been able to factorise it. I wonder what the maths is behind that. We'll have a look at that later. Let's come down and see if we can use the discriminant to tell what's happening with the graph. Okay, so coming down now. So you can tell. You certainly can, by taking b squared take 4ac and inspecting what's going to happen in your quadratic formula. So here's the equation equal to naught, and you could think of this as where the graph of this function cuts the x-axis. So let's do that in a minute. So the first thing I think you should do is a is 2, b is neg 3, as if we're using the whole formula. We don't need the whole formula here, do we? We're just going to take a peek at what's happening, and so we only need b squared take 4ac, and if we work that out, neg 3 squared, be careful there, that's positive 9. If you put this into a graphics calculator, it will not give you the correct answer, because it will square only the 3, not the negative. So you must actually bracket what you need to be squared. Neg 3 squared is positive 9, and neg 4ac. So it comes to neg 23, and that's a negative. So the roots are imaginary, or you could put no real roots, and therefore no x-intercepts. I want you to squeeze your work for as much as you can get out of it. So there'd be no x-intercepts for the graph of that function. So here we have another function equal to naught. Again, putting it down, a is 4, b is neg 4, c is neg 1. So b squared take 4ac is 32. So it's greater than naught. So you'll have neg 4 plus 4 plus root of 32 minus root of 32 over 2a over 8. So we don't have to go the whole way. We can just do b squared take 4ac. A powerful little tool, this discriminant. And so there's two distinct real roots here, and that means two x-intercepts. It cuts the x-axis twice. Powerful stuff. Good mathematics, isn't it? Let's come down, and I want you to have a go yourself here at a couple of problems. So have a go at those. Just notice here I've underlined it, 4 root 2. Be careful with that one. But I think you should do all of them and make the comment about the number of roots and nature of the roots, and also what that means about x-intercepts. Just reinforcing that. All right. Pause it, have a go, and check each answer, toggle 4 and look at the answers. I'm going to show you those answers now. So there they are. Okay, so check your answers and make sure, and you could even draw the graph with technology and just have a look at what's happening there. Okay, let's go down and have a look at this perfect square business that Hayes and Harris mentioned. So if b squared take 4ac is a perfect square, hey, you'll be able to work out the root of this. It will be a whole number. Okay, so this will be down here a whole number. So your answer will be neg b plus or minus some whole number over 2a. So this is going to either work out exactly if this divides into that, so that'll give you an integer or a whole number answer, or a fraction. But there won't be any roots in it. So it'll be rational. These are called rational numbers, no square roots in them. Okay, integer is a rational number because every whole number can be written as itself over 1. A ratio of integers. And a fraction is a ratio of integers. So that's where we get the idea. If it's a perfect square, it's going to be rational then. Alright, and what comes out of factorising? Well, when you can factorise a function, okay, like this, you might have 3x plus 1, x take 5. If there's only unity in front of x at 1, this will give you an integer answer. It'll be whatever the opposite sign of that is as you solve that little equation. And in this one, if you put this equal to naught, you get neg 1x would be neg a third. So that would be a fraction, or that would still be rational. So when you factorise, you always do get a rational answer. So that's the implication up here. If it's a perfect square, it's going to come out to be a fraction or an integer. That's going to be a rational solution, and that's what you always get out of factorising. So you can use the b squared take 4ac to detect whether you can factorise something. Now that's interesting. Come on, let's have a look at doing that now with an example here. So we'll just come down here. Alright, so let's have a look at this. A is 2, b is 1, c is neg 3. So b squared take 4ac is 1 squared take 4 by 2 by neg 3, which is 25. Oh, that's a perfect square. So this should be factorisable, and there should be rational roots. So we can say here implies rational roots, that's whole numbers or fractions, and it would be factorisable. Let's have a look at them now. So if we look at the formula, x equals neg b plus or minus, we just worked out b squared take 4ac over 4. So it's neg 1 plus 5 over 4 and neg 1 take 5 over 4. Okay, so the first one here, this comes to 4 over 4 or 1. This one comes to neg 6 over 4 or neg 3 over 2. We could cancel it. Okay, so you can see it will always give a fraction or a whole number, because the root will disappear if that's a perfect square in there. Okay, let's do it the other way. Let's try to factorise it, because if these are the answers, that's typical, the typical answers coming out of two linear factors. So let's use the reverse of FOIL. This is quite an easy one. Numbers multiply together give 2, so it'll be 2x and 1x. Numbers give 3 and 1, so I put them there. Let's try that. And if I have plus and take, I'll get neg 3, which checks. Then I get 3x, take 2x, to give me 1x. So we'll just reverse FOIL here. Don't need any really complicated factorisation techniques. Now, when a product of factors is 0, one of the factors is null. It's a null factor law, either that one or that one. So we get 2x equals neg 3, x is neg 3 over 2, or x is 1. So it checks. So you see how it works? Looking behind the mechanics of the subject to why it actually works. That makes maths more fun. Get up close and personal with it, rather than just trying to remember how to solve a problem. Alright, come on down now and let's have a look at you trying something like that. So here we are. By using the discriminant only, determine which of the following quadratic equations have rational roots, which can be found by factorisation. And you might try your hand at factorising some of these, like I did that one up there. But all we want to do here is to look at b squared take 4ac. Don't work out the actual solutions as such. Use b squared take 4ac to take a peek at it and realise then what is going on. Could you have factorised it? Okay, all right, I'll show you solutions now for those. So pause it here now, have a go, and then toggle forward to check your solutions as you do them. So here they are. They are the ones that were perfect squares, and therefore you could have factorised them. Okay, one more little thing to do, and before you build all your skills to the point we need to use our mathematics in problem solving. And that's the exciting, fun thing in the next presentation. All right, what about if you have an incomplete quadratic equation? Either a coefficient is missing, or in this case, a constant down the end is missing. What must m be if you want it to touch the x-axis, or for this equation to have a repeated root or a double root? What much must m be if it's going to have two real roots or two x-intercepts? And what must m be if you miss the axis altogether and the equation has no real roots, imaginary roots only? Okay, so first of all, same thing. A is 1, B is -2, and here's the interesting one. C is m. Okay, so your b squared take 4ac, b squared take 4ac is 4 take 4m. For a double or repeated root, the discriminant is 0, so it's 4 take 4m. So 4 equals 4m. Right, moving the 4m across the other side. Divide both sides by 4, m equals 1. Okay, two distinct real roots, the discriminant is greater than 0. So 4 take 4m must be greater than 0. Now you could do it this way, -4m, subtract 4 from both sides, then dividing an inequality by a negative, it reverses. Do you remember that? Okay, I might have a look at that, explain that to you in a minute. Or you could make it easier on yourself and, as they did over here, add 4m to both sides. Okay, so it becomes positive, then dividing by 4 gives you m is less than 1, reading this way. The same as this, but you're reading the opposite way. So you can do that. Let's pause over here and look at that rule. The rules for solving inequalities or inequations are the same as equations, except for one thing that you can't do, and that's multiply or divide by a negative. Why is that the case? Well, let's look at this. Let's draw a number line and say that we've got -2 and 1, and that's 0 on the number line. So 1 is greater than -2. What does that mean? Greater means lies further to the right. Now if I multiply both sides or divide both sides by -1, this will be -1 and this will be +2. Now multiplying by a negative does what? It reverses, multiplying or dividing, it reverses the position on the number line, doesn't it? All of a sudden now the 1 becomes -1, so now it's over here, and the -2 becomes 2. Can you see that multiplying or dividing by a negative is going to change their relative positions on the number line? So now -1 is less than 2 because it's further this way. Greater than means further to the right algebraically in maths land. And to the left, further to the left is less than. So this multiplication or division by a negative changes their relative position on the number line, and that's what this sign means. The greater than or less than sign is talking about position right or left of another point on the number line. Okay, do you get it? It's pretty simple mathematics, but I'd like you to get up close and personal with that rather than just learn the rule. Multiplication or division by a negative, you change the sign. You see what I mean? Okay, I want you to do all of these and think about what that means for x-intercepts as well. As you create, through these different m values here, different functions, then you might think about what the graph would look like. So here what we've got is a little picture up here. You've got a double root when m takes that value to make discriminant 0, and on this side we've got two distinct real roots, on this side imaginary roots. So there's a whole lot of m values that when you stick in there will fall in one category or the other. Okay, so range of m values. Alright, have a go, and I'm going to show you the answers. Come on down now. Here are some answers. And that's it for me for now. And I'll catch you in an exciting presentation coming up, which is on problem solving. It's going to be fun using all your skills. Cheers for now.